Okay, and so what did you get out of our discussion? Again, still slip?
You can determine the coherence of
Yep.
a beam of light from it.
How do you determine temporal coherence?
Look at the irradiance. Right?
Well, yeah.
Yeah.
But the time axis maps onto the x-axis.
Okay.
The point of the observance.
Yeah, so the envelope of the interference is the coherence.
So remember?
So the envelope of the interference is the coherence. And you can calculate it using visibility, you know, the IMAX, IMIN business. Okay, and we talked about spatial coherence. Okay, so what we want to do today is, first of all, I'll give you a couple of other examples of division of wavefront. And then we're going to get into division of amplitude. So, there's something called Lloyd's mirror, which, when you see it, it's just trivial. Take a mirror, and let's say you have some source right here, and that source is going to irradiate light, and the light, this incident on the mirror, of course, reflects from the mirror. No big surprise. So we have light propagating this way from reflection, but in that region, we also have light propagating this way directly from the source. So in the region of overlap, we'll get interference. And I think Dr. Schultz's group used to create interference fringes this way. They'd record the fringes in photoresist. At any rate, that's Lloyd's mirror. There's also something called Fresnel's mirror, or mirrors. Oh, and by the way, no, I won't mention it. So if we have, say, a pair of mirrors, something like this, and we've got a point source, and the light from the point source that goes on this mirror reflects off this way, and from this mirror reflects off that way, and you have a region of overlap where they're going to get interference. And what you can do is unfold the path of the mirror and find the virtual point source for each of these guys, something like that. And now it looks like you have two sources, or two slits. And this one up here, you can also unfold it. And again, it looks like you have two sources. So, one way of doing, or two ways of doing division of wavefront. There's also Fresnel's biprism. And in that case, you have a point source, and then you've got a prism like this, and light that's incident on the top of the prism refracts down, and light incident on the bottom of the prism refracts up, and again, you have a region of overlap. And if you project back the virtual point sources, then basically it looks something like this. You have two virtual point sources. Okay, so some other ways of doing division of wavefront. Okay, let's get rid of that and now start on division of amplitude. Okay, so what we're going to do with division of amplitude is consider, as an example, the case of a dielectric slab. So let's say that we've got a slab of refractive index M1, no, let's make it N2, immersed in a medium of refractive index N1. And let's say that we have a plane wave instant, and we're only going to consider one ray of the plane wave. Then when it hits the front surface, we'll get a front surface reflection. So let's show it like that. And when it hits, and then the rest of it will refract and go through. And when it hits the back surface, some of it will reflect. And then at the front surface, most of it will refract and transmit like that. And so we're going to neglect what's transmitted over here, and we're going to neglect any bouncing around of further reflections. So we're just going to consider the front surface reflection and the back surface reflection, and the reflection is just due to Fresnel reflection. And what we want to do is have these two things interfere, so we need to bring them together. Let's use a lens, and then in fact, yeah, let's do it that way. So the two rays come in, and if we look in the back focal plane of the lens, it's going to bring those two rays together in the back focal plane. Why does it bring them together in the back focal plane? So parallel rays here get focused to a point in the focal plane. So a lens, in some sense, is an angle to position converter, meaning that this is the back focal plane. Any light that's incident parallel to the axis will focus down to that focal point. On the other hand, if I have light instead at some angle, like this, and I consider those individual rays, they'll all be focused down to a point in the back focal plane. So the lens is acting as an angle to position converter. And if we flip it around and start off with a point source here, then it's basically a position to angle converter going the other way. So here we're using the lens as a angle to position converter to get light from the two rays to overlap. Okay, so we have interference here at that point for light propagating along the two rays. And with that interference, notice that the rays propagate along two different paths. There's the front surface reflection, the back surface reflection. So there's going to be a path length difference, which suggests there will be a phase difference. Okay. Now the question is, if I want to calculate what the interference is here, what do I do? What's the first thing I have to decide? Which model? Okay. So which model shall we choose?
Scalar.
Scalar? Can we treat reflection and refraction with the scalar model?
Well, it depends if you want to use the TE versus TM stuff.
Yeah, so remember with reflection and refraction at a single interface, we wanted to answer two questions. One, what direction does the reflected and transmitted light go given the incident light? And two, how much of the incident light is reflected and transmitted? How much in terms of field, how much in terms of irradiance? Okay, so did we need to use the electromagnetic model to answer either of those questions? I mean, how did we set up answering those questions?
So with the direction no,
So how did we answer them? Where did we start?
Repeat the question.
So for light incident on some interface between two dielectric media, what direction is the reflected and refracted rays going, and how much of the incident gets reflected and refracted? So how do we answer that?
Start with the EM model and plane waves.
And then we applied what? Boundary conditions. So it all fell out of the boundary conditions. Does the scalar model have boundary conditions? Nope. No boundary conditions. That's something that is specific to the electromagnetic model. So can we use the scalar model here?
No.
We cannot. Now it turns out, upon further inspection, that with the scalar model, you actually can get the answer to the first question, what direction is the reflected and refracted wave? But you cannot get the answer to the second question, how much is reflected and refracted? You have to use the electromagnetic model. So here, do we care about how much is reflected and refracted? Yeah, we care a lot, because that's going to tell us how much field we have in each of these to interfere with. So which model do we have to use? We have to use the electromagnetic model.
question, having a lens in there, is we took 661, and so we did like thin lens things, but we also made like the ray optics approximation. Where does that fit in with the scalar model and the electromagnetic model?
So with the ray optics model, I mean, basically there, you have some
Got a really short wavelength and
optical system. You have a source here, and you want to know for light coming out of that source in some direction, where does it end up over here in the output space? And the way you find out is you basically apply Fermat's principle, which says that the time of flight between here and wherever it ends up is going to be over the path that minimizes the amount of time it takes to get there. And that's the basis of ray optics. And so that's actually what gives you the refracted angle at each of the interfaces. And then based upon that, you can figure out what a lens does, what a prism does, etc.
because there were a lot of interfaces, much like this, but we never did, well, until we got to diffraction, we didn't do electromagnetic stuff.
Yeah, well, and diffraction is the scalar model, generally. So, yeah, so with respect to the effect of the lens, all we're caring about is the fact that it does this,
Okay.
angle to position conversion. And why do we care about that? Well, these rays, they're parallel. That means they'll never come together. So how do we get interference between the field in ray 1 and the field in ray 2? We need a way of forcing them to come together and be spatially coincident. And that's the purpose of the lens. It's its only purpose. Just bring those two things together. Okay, so we have answered which model we should use. Now, what's the next thing that we do? What's the next step?
Get the field.
Write down the fields. Okay, and whenever we write down the fields, we're writing down the fields at some location in space. So here, what's the location we ought to write down the fields for?
We care about is half the focus where we think they're going to interfere, right?
Yeah. So we'd want to write down, let's say this is path 1 and path 2, we'd want to write down the fields here, E1 and E2, and then in general, their vector quantities. Okay, now, if I consider a plane here perpendicular to these two rays, so perpendicular, the path length from here on following path 1 to this point in the focal plane, and the path length from here following path 2 to the focal plane, are those paths different in terms of how much phase the light picks up? Yeah, they're not. They're the same optical path lengths, which goes back to how the lens works in the first place. So what that means is that whatever phase I pick up going from here to here on path 1, from here to here on path 2, it's going to be the same phase. Which means when I take the phase difference, it's going to go away. So I could actually, instead of writing the fields right here, I could write them right here and right here, and I'd get the same result. But if I'm going to write them right there, why don't I write them back here and just eliminate having to worry about all that stuff? Yeah, that seems like a reasonable thing to do. Okay, so let's take this region and draw it a little bit bigger so we can get some detail. So here's our slab, and let's say it has thickness D, refractive index N1, it's immersed in something with refractive index N2, immersed in refractive index N1 medium. And then over here we can draw that we have our ray instant at theta 1, and then we have a reflection, front surface reflection at theta 1. We have transmission at theta 2, and reflection at theta 2. And then we have refraction at theta 1 again. So we're happy with that picture? Okay, so let's label some of these points so we can talk concretely about them. Here, let's label this point B and this point C, and then let's put in our perpendicular here. So let's label this point D, and this point right here we'll label D prime. Okay, and then what's the angle right here?
Minus theta 1. Which one?
This one right here?
It's like the one, right?
Theta 1. So it's yeah,
Why
it's
not?
theta 1. This one right here, that's theta 1.
Oh, yeah.
This
Oh,
one is
oh, oh.
90 minus theta 1. Okay. Okay. So now that we've got our little diagram, let's write down the fields. So let's make life a little easier on ourselves by assume that we have either TE or TM polarization, one or the other. And if we can do that, then we can solve the more general case of arbitrary polarization by just decomposing them into TE and TM components. Okay, so in that case, if it's TE or TM, let's say that I write that this incident field at point B, let's say I give it the symbol E instant. Notice, have I put a vector sign on that? I have not. Why did I not put a vector sign on there? Am I being sloppy? Am I violating my own principles?
Are we only caring about the magnitude?
No. back to this.
Oh, we don't know which one it is?
Well, it's either TE or it's TM.
Okay.
In which case, we know what the direction is. So I'm not bothering to put a vector sign on there because I know the direction. It's either this way or it's that way. So whichever way, I'm just looking at all the information the field contains except the polarization. So what information does that contain?
Phase,
Magnitude, phase, and then the spatially dependent phase, except I'm at one particular point, I'm at B, so that has some value, whatever it is. So this is basically just a complex number. Okay. Does that mean question?
No, I'm just working through the cross product.
Oh, I didn't see the other fingers,
I
yes.
have, yeah, I have my hand.
Okay, all right. Couldn't figure that out. Okay, so right here, if that's path 1, that's path 2. Here at point D, I can write the field as E1, and I'll leave off the vector sign because I already know the direction. It's either TE or it's TM. And at D prime, I can write down the field as E2. Now, E1, what's it going to be in relation to E instant, the field right at point B?
It's gonna be multiplied by that reflection.
Reflection coefficient?
Yeah.
So it'll be the reflection coefficient times E instant?
Yep.
Uh-huh. Okay, and it's propagated from B to D, so what happens when it propagates?
Picks up in phase.
Picks up some phase. So let's call that E to the J phi1 for the amount of phase it picked up in propagating from B to D. Okay, good. Now, let's introduce a little bit of extra notation, because here I'm in medium 1 going into medium 2, and I'm reflecting. Let's call that reflection coefficient R12. I'm in medium 1 going towards medium 2, and I have a reflection at that interface. Which is distinct from over here. I'm in medium 2 going into medium 1. So over here, I'll have a reflection coefficient R21. And then the beautiful thing is that R21 is minus R12. Right? So you just go back to the Fresnel equations for reflection. TE or TM, doesn't matter, just pick one and swap all the substrates, or the subscripts rather, and you end up with that relationship. Okay, so now let's figure out the field here at point D prime, which is E2, having subscripted this with R12. So what will this be in terms of the instant field here?
R times T.
There'll be 2 T's and an R.
Okay, so let's write them down. T what?
1, 2.
T12,
R21.
R21,
T2, 1.
T21, and then E instant, and then what?
Do we say 0 phase?
Well, it propagates from here to here to here.
It's got a lot. It's got a lot.
Yeah, so it's gonna pick up some phase. So we'll just call it P2. Okay. Now let's introduce a little approximation. T12, T21. Let's say that N1 is not very different from N2. Then it turns out the T's are going to be really close to 1. So this is going to be close to just R21, E instant, E to the J, E2. And then R21 is minus R12, E instant, E to the J, E2. And a minus sign is just e to the j pi, so this is r12, the instant e to the j v2 plus pi.
Why did the t's cancel out?
They didn't cancel out, we just said, hey, this is going to be the case, so they're really close to 1.
Oh, okay.
So we're approximating these things as 1. Which it turns out is a really good approximation. Okay, so I have the fields, and I can write down the interference, but before I do, let's first of all look at that phase difference. We need to figure it out. So basically, I'm going to have here, the phi2 path is going to be the line segment BC plus CD prime, right? That's that path here. And that's in material N2, or material that has refractive index N2. So it's the optical path we care about, refractive index times physical path. And then over here, I'm going to go from B to D, so minus N1 B to D. And then all of that is 2 pi over lambda naught, turn it into a phase. And remember, when we propagate positive distance, we pick up negative phase. So it's minus 2 pi over lambda naught. Yeah.
On the bottom equation for E2, we have e to the j T2 plus pi. Is that P2 plus pi supposed to be in the print? Okay.
Yes, thank you very much.
Just wanted to double check.
Yep,
That's-
you're absolutely right. That's important. Yeah. Good, okay. All right, so now we need these line segment lengths. Notice that BC is equal to CD prime. And it's the same length. And then if we look at this triangle here, that's theta 2. This is D. So this length right here is evidently D over cosine of theta 2, just using trig with that triangle. So basically we're calculating the hypotenuse knowing this distance D. Are we all good? Okay. All right. So this piece right here is going to be 2 times D over cosine theta 2. So that leaves us with BD. And BD is this length right here. We've got a theta 1, we've got this triangle. So what we can say is that BD is going to be BD prime times sine of theta 1. Do we believe that? So here's BD prime, the hypotenuse of the triangle. Then this length over here is going to be the hypotenuse times sine of theta 1. We good with that? Okay. Now notice BD prime is twice the distance from here to here. Okay, and that's part of this triangle we've already been playing around with. So that then, this piece then is basically 2 times D tangent of theta 2, and then we've got this sine of theta 1. Okay, so we plug this in for the second term here for BD. And now we've got something that's kind of a mess. But if we substitute in with Snell's law, we can simplify it dramatically. And once we do that algebra, what we end up with is 4 pi over lambda naught n2 times cosine of theta 2 times d. So that is the phase difference. Okay, this term right here is going to become your best buddy. You're going to see it over and over and over again. Yeah.
There's no negative on this, right?
Oh, yeah, actually there is. Thank you.
Okay.
But it turns out, because it's in a cosine, cosine of a negative is the same as cosine of a positive. It's going to go away. We don't care. It's not going to matter.
Technically, yes, but it doesn't matter. Okay.
Yes, that is right. Yes. Okay. Yeah. So now we can write down the irradiance due to interference. And so what's the irradiance going to be?
Field magnitude squared divided by intensity.
So I1 plus I2 plus 2 times the square root, I1, I2 times cosine. And now this cosine, we have delta phi plus pi, right? Because of this pi over here. And maybe, yeah, okay, let's just call it that. Okay, so if we take that pi, that gives us I1 plus I2 minus 2, square root, I1, I2, and then cosine, and then we have the minus 4 pi over lambda naught, 4 pi over lambda naught, n2 d cosine theta 2, and cosine of a minus is cosine of a positive, so we'll just drop the minus sign right there.
So that minus came from the pi, right?
Yes, this minus came from the pi.
Okay.
That's right. Okay. So, notice here the magnitude of E1 and the magnitude of E2 are the same. So that means I1 is equal to I2. So here I've got 2 times I1. Here I've got 2 times I1, so I can write 1 minus cosine of 4 pi over lambda naught n2d cosine theta 2. So that then is my interference. And this thing right here, I'm just going to call it delta phi, which is the same as this delta phi, but the minus sign's gone away. But I'm just going to call it delta phi. So this then becomes 4 times I1 sine squared delta phi over 2. So that is the expression for the irradiance at this point. Now notice that the irradiance depends on what? Well, it depends on theta 2. And for given n1 and n2, theta 2 depends on theta 1 through Snell's law. So this interference term, or the interference, depends upon angle of incidence. It also depends upon the thickness of the slab. It depends upon what refractive index we've got relative to whatever medium we're immersed in. And it also depends on wavelength. So change any of those things and you change the irradiance. Yeah?
So for our approximation, we did N1 is approximately N2. How close of an approximation does that have to be? Like,
If N1 was air and N2 was glass,
that's fine?
totally fine.
Okay.
Really?
Uh-huh. Yep.
But
Which means the reflection coefficient is 0.2.
are we assuming angles are not? Or
Any angle. Well, I mean, any angle so that I mean, the bottom line is that the front and back surface reflections are not very big. How big is not very big? 4% or transmittance or rather reflectance. So air glass, you get 4% of the power reflected. That's not big. I mean, we're working in fields.
We're really thinking that most of the light is lost through this thing.
Yeah, most of the light just goes straight through.
Most of it goes through, so we're just in the small portions.
Yep. Yeah, so these two surfaces are just picking up a little bit of the power. Yeah.
That was a 1 minus cosine there. Was that meant to be a cosine squared?
No, 1 minus cosine. Yeah, and then there's a half angle formula that would apply. Yeah. Okay, so, great.
So this isn't really like a intentional interference setup we're designing here, it's more like the interference that would come off of like just an optical system that we wanted to use.
Yeah, just what comes off a piece of glass. You know, basically any dielectric slab. Yeah.
Does it have to be N1 and 2N1, or do we have a N3 on there to maximize?
We're gonna do that one later.
Okay, so we will.
We're gonna see exactly where that goes, and that's gonna lead us into anti-reflection coatings, Bragg mirrors, and all kinds of other fun things.
Oh, fun.
Yeah. Yeah, all thin film phenomena is basically that. So we'll see how this changes. Yeah, it's a fun place to go. But to get there, first of all, we're just looking at the simplest possible case. A dielectric slab immersed in some medium, and the refractive indices aren't very different, so we only get a tiny amount of reflection on the front and back surface, and then we see what happens. Later, what we're going to do is say, well, let's say our reflections aren't necessarily small, and so we're going to have to take into account all of the multiple reflections here and see how that adds into the situation. Okay, so now what we want to do is apply this and see what this means in practice. And to do that, I'm going to introduce you to Haidinger fringes. And kind of the classic setup to observe Haidinger fringes. And what are Haidinger fringes? Well, you'll see. And once you see those, then we'll do Fizeau fringes, and then we'll be able to see what's the difference and how do you observe one versus the other, does it mean anything, etc. So let's say that we have our dielectric slab over here. So N2, N1, N1. And let's say that we have here a monochromatic extended source. What does that mean?
That's our point. It's like,
Yeah, monochromatic means
one frequency.
one frequency. Extended source
Yeah, it's like spread out.
means you have a whole bunch of point sources, and these point sources are independently emitting, meaning that they're not correlated with each other. So even though we have monochromatic light coming out of this thing, if you compare the light from 2 point sources, it's not going to be coherent.
So, like when the fluorescent bulbs up there wouldn't actually be an extended source
Well,
because the light
it's
would be
not
coherent.
monochromatic.
Oh, okay, yeah, that
I
too,
will show
but-
you an
okay.
example of one of these in just a moment.
Okay.
Actually, after we talk about Fizeau fringes, we'll look at it. Okay, now let's say that I have a beam splitter up here, and I'm only showing you the partially silvered surface of a piece of glass, because that's the thing that's going to generate the reflection. So let's say I look at a point source here, point source 1, and I look at light coming off in this direction. So I'm only considering that direction. So a ray in that direction, it reflects, and then it's instant at some angle theta 1 here on the front surface. So I get a reflection. And then it comes through that beam splitter. And I'll also have a transmitted portion of the light, and I'm going to consider its reflection from the back surface, and you can ignore everything else, and then it's going to come out parallel to that first ray. So, propagating like this. And this guy, that guy. Okay. So, over here, I put a lens. And so this light comes into the lens, and the lens focuses it down into the back focal plane. And it just goes somewhere. That's not where I want it to go. So it just gets focused down to some point over here. Okay. So clearly, light from this source going in this direction is doing exactly this thing right here that we drew, right? So what's the interference going to be right here? Just that. So we just have to calculate what theta 2 is, know what D is, the other parameters, and voila, we'll know what the irradiance is at that point. Yeah.
What's this angled?
That's a beam
interface?
splitter.
That's a beam splitter.
Yes, so. And it's on a piece of glass. It's the partially metallized surface on a piece of glass. Okay. Now, let's say I consider a second point source over here, and I consider a ray coming off like this that's parallel to that first ray from the original point source. Then I consider the reflected part. It's at an angle theta 1. Some of it reflects from the front surface, some of it reflects from the back surface. And notice over here it's parallel with the light from point 1.
So it's focused the same.
So it gets focused to the same point. Now, does light that follows the green pair of rays from point 2 interfere with light that follows the black set of rays?
No.
No, absolutely not. So do I have an interference over here?
Only for itself.
Only for itself. So basically I have light from the 2 green rays interfering here. I have light from the 2 black rays interfering here. And each of the interference terms we can write this way, and the irradiance for each one. But because they are incoherent, mutually incoherent, those 2 irradiances just add. If they were coherent, we'd have to add the fields. But they're not. They're incoherent, so we add the irradiances. So, that's kind of weird, but it works. It's what you observe. Okay, so here's the point I want to get at. Well, 2 things really. Number 1, if we only consider light from this point source following the black ray, easy enough to calculate what that irradiance is. Now, what if we considered all the other rays going off at other directions, and we looked at what irradiance we form in this plane? And let's say we draw it this way, and here's the x and y axes of the plane, so this plane right here, x, y. Question is, what will the interference pattern look like for light coming from point source 1? Rings, and why? Let's say you were right here, and you traveled radially outward. So we're right here. We travel radially outward, what would we see?
Like a cosine or something. It's gonna be like
So if we travel radially outward, basically what's changing is theta 2, right?
yeah.
Because theta 1's changing. Okay, so it's basically this is a function of theta 2. So it'll be something. Whatever that functional relationship is. Okay. Now, what if instead of going up here, I came out? So instead of going up this direction, I come out this direction. What will I see?
So when you say an extended source, is it like a line or is it like a?
We're considering light only from that point.
Okay. So we're just basically sweeping the angle the other direction.
Yeah, so instead of sweeping the angle this way, we're now
And
sweeping the
outward.
angle this way.
Okay. I feel like it'd be the same thing, right?
It is the same thing. Yeah, we get the same thing. And basically, it doesn't matter what direction we go here,
And that's why it looks like rings.
that's why it looks like rings. So basically, we get, fringe here, fringe here, a fringe here.
So the dark spots are just all those maximas, the light spots are the minima.
Yes.
Okay.
Yes. So we get a set of concentric rings. So that's the interference pattern that we observe from just a single point source. And the circular symmetry of the pattern comes because the lens has circular symmetry. Okay, so now if we consider light from point source 2 just by itself, what pattern will we see? Exact same thing. So that means the pattern from point source 1, that irradiance, is just added right on top of the pattern from point source 2, which is added on top of the pattern from point source 3, 4, ad infinitum. So all the point sources generate exactly the same interference pattern, and the intensities all just pile on top of each other. Yeah.
So the purpose of the beam splitter is just to create different length pathings, pretty much, because
The purpose of the beam splitter is if we didn't have the beam splitter here, we'd have to take our extended source and stick it right here. And then the light really can't come back through the extended source. So the only thing we're doing at the beam splitter is just taking our source and moving it off to the side. That's the only purposes for it.
And we're losing like however much power each of those interfaces with the beam splitter, right?
Yep.
Okay.
Yeah. Yeah, if it's a 50-50 beam splitter, we lose half the power at each
Each
pass.
reflection.
Yeah, so we end up with maximum a quarter of the power times whatever the reflection coefficient is on these guys. Yeah. Okay, so the point here is that this setup before the lens generates a bunch of parallel rays. And to get the rays to interfere, we had to use a lens, and we had to look in the back focal plane of the lens. So let me say that a different way. The light interferes at infinity. And to bring infinity to a finite distance, we stick in the lens, and the finite distance is the back focal plane of the lens. So Haidinger fringes are characterized by a setup where the setup creates parallel rays, and you have to use a lens and look in the back focal plane of the lens in order to see the fringes. That's the setup for Haidinger fringes. Any situation that gives you parallel rays and you need to use a lens, look in the back focal plane, that situation is generating Haidinger fringes.
And the fringes are the pattern,
Mm-hmm. Yeah.
but if they're all kind of if there's a whole bunch of incoherent point sources and they're all on top of each other,
Mm-hmm.
where do you actually ever see that pattern?
Oh, if you look at only a single point source, you get that concentric set of rings. And then you turn on another point source, you get the same set of rings, it's just right on top of each other. So you still see that set of rings. Turn on another point source,
Oh,
the-
yeah.
the irradiances are just adding right on
It's
top
just
of
like
each
it'll
other.
look brighter and brighter. and brighter.
That's it.
Okay.
That's exactly it.
So that's the only thing that, using the extended source versus
Yeah.
point sources, just so you can actually see it then.
Yeah, pretty much. Yeah. But it brings up an interesting point that you can still get interference with an extended source that has limited spatial coherence. And here you can see exactly how you get that interference. Okay, so now let's do a setup for Fizeau fringes. Well, we're going to need a lens again, but what we're going to see is that the lens serves a different purpose. Okay, so here, let's say that you have a little wedge of material. And actually, let me draw that differently. I need to move down the board. Let's say you have a little wedge of material, and it's of refractive index N2 immersed in a medium of N1. And let's say that the wedge angle is alpha. And let's say that we have a beam splitter here, and we have some source off to the side. I'm just going to look at one ray coming in. So let's say that ray comes down here, and then clearly I'm going to get a reflection. And it's going to be off at an angle, right? Because it's hitting this slightly tilted surface. And then I have light that goes through, and then it's hitting a surface that's at a slightly different angle. So it's going to come off at a little bit different angle. Okay, so in other words, these two rays are not parallel rays. They're coming from a very small region in space, namely right there. So, if I take a lens, so I can force these two rays to come together, so force them to come together. One question is, the plane where they come together, is that the back focal plane? No. What is it?
It's whatever the distance on the front was, right?
Well, basically what we're doing is we're fulfilling the conditions required for imaging. We're taking this object plane and we're imaging it to this image plane. So this lens is not taking parallel rays focusing to the back focal plane. Instead, it's taking some object and imaging it. So the lens is fulfilling the imaging condition. And in doing so, it brings together these two rays so that they interfere. Okay? So we could, just like we did for the dielectric slab, we could set up similar equations for path 1, path 2, assume TE or TM. And bottom line is that we'll end up getting the same expression for the irradiance here. 4 times I1 sine squared delta phi over 2. And now delta phi, though, is a little bit different. Delta phi basically goes back to this path length right here. And so with that path length, it's basically 2 2 pi over lambda naught times 2 times n2 times d, where d is just that separation at that point. And the 2 is there because the beam 2 goes through that length twice.
So that second term is delta phi, right?
So this is okay. And then if this truly is a wedge, then d is basically alpha times x, where this distance is x.
There's the paraxial.
Yeah. Yeah, it's a small angle approximation. So if I were to take a look at this wedge, let's say the wedge had this shape, this is x, then basically what I would see are a series of fringes like this as I go along an x.
That's in the imaging plane, or is that on the wedge?
Well, it's what I would see here, the image
Because
of
it's
that
the same,
wedge.
right?
Mhm. Yeah, with whatever magnification factor the imaging system is giving us. Yeah. So I would just see a set of linear fringes for this linear change in thickness. Okay, so Fizeau fringes, we get those when we have to image a region of, in this case, physical thickness variation. Now, it turns out you all are very familiar with Fizeau fringes, because when you have a soap bubble and you see that colored set of fringes, those are Fizeau fringes. It's basically a reflection from the inner and outer surfaces of the soap bubble. Or if you're walking in the parking lot after a rain, and there's always the spot in each parking stall where engines have dropped their oil, and you see this shiny, colorful sheen. That's basically Fizeau fringes in the oil layer that's on top of the water layer. Also Fizeau fringes. So it turns out you see these things all the time. Okay, now what we want to do is look at some Fizeau fringes. So I brought a setup over here with which we can do this. So someone want to turn out the lights?
You want 1 or 2?
Let's try 2. Okay. Is there power on that? I don't know if there's power on this.
There is power on the
There it is,
floor.
'cause I've used this.
There's power on
Thing here.
these.
You probably hook it there and just gonna hook over.
Oh, you have used the stapler over here?
Yeah, you can
Borrow the stapler.
Yeah, maybe that.
No.
Oh, yeah, I feel warm.
Probably.
There we go. Okay.
You good on lights?
Yeah. I need some black paper.
Some of my desk, I can grab real quick.
Yeah, that'd be great. So the reason for the green color is this is a fluorescent lamp where the fluorescent species is a particular molecule that emits, there's just one electronic transition state. And so that means it emits with a very narrow bandwidth. That means it's highly temporally coherent. Okay, so I'd say let's come over here, guys. Oh, yeah, that's very helpful.
Oh, yeah.
So we have a little cover slip here. And see if you can get in there and see, can you see fringes?
Yeah. You can kind of see them up here too.
Yeah, you can see them up there. So I'll let you hold this guy, and then another thing you can do is take a glass slide, put these together, and then change how you're pressing on it, and you'll see the fringe pattern change. So give it a try.
So that's what happened.
Yeah, exactly.
The screen's not on.
Yeah, that's right, there's a tiny air gap. Okay, go for it.
You can actually see these on the build trail
Oh, yeah,
parts window.
all the time.
Yeah.
Mhm.
Is there still a monochromatic assumption for these Frizell fringes?
Yes.
So is this actually a monochromatic source, or
Yeah,
is this tight enough, or?
yeah, it's very monochromatic.
Okay. This is the one that was in the lab, right?
Yeah.
I always wonder what that box was. I just see it sitting around like, what's this?
Yeah, I got it so that we could actually characterize the gap between the Teflon film and the quartz.
Oh, okay.
That was the original.
That makes sense.
So for the colorful sheens that you're mentioning, like on bubbles and oil surfaces, that's not monochromatic.
Correct.
So is that how, I guess I'm not seeing where the
So what's
fringe part
happening
comes in.
is when you see colors there, the colors are always spatially separated.
Yeah.
And in other words, they track the thickness variation of the film. So we're given thickness variation, a color will interfere constructively. So you'll see that. And then you move a little bit over, and now you have a different thickness. A different color is going to interfere constructively, so you see that color.
Okay.
So that's how it's working.
Is that kind of like general nature of a prism type idea, or?
We'll talk about prism shortly.
So I think I missed it, but like with this beam splitter, with the Frizell fringes, is it like just like slightly, breaking them or?
No, it's just, you got a ray coming in,
Oh, okay.
and it reflects, and then here, this is a wedge, so the reflections from the two surfaces go off at two different angles.
Okay, I totally missed that. I thought that was just like a plane that you were just
Oh.
stating. So yeah, okay, so that makes sense.
Yeah, and the only purpose of the beam splitter is to be able to take the source and stick it off to the side.
Okay.
That's the only thing it does.
So in this setup over here, I guess kind of what corresponds to what?
So basically, the glass cover slip is here, and the glass slide is here, and we have an air gap. So we got N2 is actually air, and N1 is glass. And then if you just take the cover slip all by itself, you can see interference fringes.
In that case, is the cover slip the N2?
Yes. And air is N1. And if you see fringes, what that means is that the thickness of the cover slip is not uniform.
How down to like how far?
So, and that's easy to calculate knowing the wavelength of the source.
Okay.
You can calculate it exactly.
So you can essentially figure out how big air bubbles are within it.
Oh, yeah. Oh, yeah. I mean, to within, easily a few tens of nanometers, you can figure out the thickness.
That's really nice.
Yeah, just by looking at the color of what's coming off. Yeah, and when I was a grad student, it turns out we used to use this one of the guys in my group actually, he would grow BSO, bismuth silicon oxide, which is a photorefractive material. It's crystal. He'd use this Chokowski growth method, and then he'd end up with this boule of material that he grew, and then he'd saw it and polish it. And to know how good he did on the polishing job, he would use something like this with an optical flat. And so the optical flat, its purpose is to have just a really flat surface, so that is your reference surface. And then if you put one of these BSO crystals on here that he's polished, let's say it did something like this, and then you look at it, look at the fringe pattern. So looking from this direction, you see the BSO crystal. If you had a really good polishing job, you'd see fringes that would do something like this. Okay. And so what would that mean if you have fringes like that?
So it's pretty flat in the middle and it curves a little bit on
Yeah,
the edges.
really flat here, curves on the edges, which is typical with polishing. When you're polishing, the edges tend to get rounded just a little bit. So he would use this method all the time to figure out how good of a polishing job he'd done. Another thing that this gets used for a lot is to measure the quality of an optical component like a lens. So if you take a lens and stick it on there and look at it, then you'll see a series of fringes because you've got this curved surface on top of a reference flat surface. And by looking at the shape of those fringes, you can tell how good the lens is and what kind of aberrations it has. And that's called Newton's rings. And we won't go through the details of it, but it's another application of the fringe situation. Okay, so
as you move up the wedge, are those fringes uniform? Or do they get brighter, pretty even?
As long as the wedge angle's small, they're pretty uniform. Yeah, just like when you see these, they're pretty uniform. Yeah. Okay, well, it looks like we're about out of time. So next time what we're going to do is we'll start with a Michelson interferometer. And what you're going to see is the Michelson interferometer duplicates this situation. It generates Haidinger fringes. So we'll see how that works. And then we'll look at a different configuration of the Michelson interferometer and explore some of the subtleties.
Cool.
Okay. Yeah, because Michelson interferometers are really useful lab instruments, as are Mach-Zehnder interferometers and other types of interferometers. So you come across them a lot. All right, everyone. Well, enjoy doing the homework. Do a week from Tuesday.